In the session, we discuss about communication link analysis. In the figure, we see that a simple block diagram representation of a wireless communication, it having transmitter, channel as well as a receiver. In that, some of the blocks are optional and some of the blocks are essential, depend upon availability of the information source. In the communication link analysis, we discuss about a few sections. In that, section number 1 regarding about what the system link budget tells the system engineer. Second one regarding about the channel. Third one, received power and noise power. Fourth one, link budget analysis. Fifth one, noise figure, noise temperature and system temperature. Sixth one, sample link analysis. Seventh one, satellite repeaters. Eighth one, system trade-offs. These are the topics we covered in link analysis in communication. Now moving to the link budget. So first of all, we discuss what do you mean by link. What the system link budget tells to the system engineer. When we talk about communication link, to what part of the system are we referring? Is it simply a channel or region between transmitter and receiver? No, it is far more than that. The link encompasses the entire communication path from the information source through all the encoding and modulation steps through the transmitter and the channel up to including the receiver with all its signal processing steps and terminating at the information sink. What is a link analysis? Now we discuss about what is a link analysis. Link analysis and what purpose does it serve the development of the communication system. First we discuss about what is the link analysis, then we discuss about the development of a communication system regarding about link analysis. A link analysis and its output, the link budget, consisting of calculation and tabulation of useful signal power and interfering the noise power available at the receiver. Once again I repeat, the link analysis and the output and the link budget consisting of calculation and tabulation of useful signal power and interfering noise available at the receiver. The link budget is a balance sheet of gains and losses. The link budget is a balance sheet of gain and losses. It outlines the detailed appropriate of transmission and reception of resources, noise sources, signal attenuators, and the effects of process throughout the link. Some of the budget parameters are statistical. Example, allowance for the fading of the signal. The budget is an estimation technique for evaluating communication system error performance. We examined the probability error versus signal to noise ratio curves having a waterfall like shape, such as the relation between probability error and signal to noise ratio analysis. We related to the error probability to the signal to noise ratio for various modulation types in a Gaussian noise or any other noise. Once a modulation scheme has been chosen, the requirement to meet a particular error probability dedicated a particular operating point on the curve. In other words, The required error performance dictates the curve of signal to noise ratio that must be available at the receiver in order to meet the performance. The primary purpose of a link analysis to determine the actual system operating point and establish that the error probability associated with that point is less than or equal to requirement. Once again I repeat, the purpose of link analysis is to determine the actual system operating point and establish the error probability associated with that the point is less than or equal to the requirement. That is the main point in the link analysis. Of the many specifications, analysis and tabulations that are used in the development of communication system, the link budget stands out a basic tool for providing the system engineer with overall the system insight. By examining the link budget, one can learn many things about overall system design and performance. For example, for the link margin, one learns whether the system will meet many requirements comfortably, marginally, or not at all. That means it is an examining test whether the particular all system parameters meet the grading mark or not. The link budget may reveal if there are any hardware constraints and whether the such constraints can be compensated for other parts of the link. The link budget is often used as a score sheet. It considering system trade-off and configuration challenges and in understanding subsystem lacunae and interdependence systems. For a quick examination of a link budget was done preciously or if it represent a rough estimation. Together with all other modeling techniques, the link budget can help predict equipment with the size, prime power requirements, technical risk, and the cost. The link budget is one of the system manager most useful document. It represents bottom line tally in search of optimum system performance. That means, what is the link budget? It is an analysis of entire communication part. It is not regarding about a specific channel, a specific transmitter or a receiver. It is analysis of entire communication part. That is analysis of signal, analysis of interference, analysis of ISI contributions and etc. And it is also including gain and losses produced by the transmitter and as well as receiver. And coming to the link budget, it's an estimation of the input and output system performance. That means we have to give a mark value to the system performance to estimate on estimation base. Estimation base means on base of probability. Will the message get communicated or not? Yes. Based upon the link budget, we have to finalize that will the particular message get communicated or not. And last one, what are the trade-offs can be made and what is the effect they will? What is the effect will they have? So finally, these are all the questions can be answered by a simple topic that is called link budget. Already told that it is not an analysis of a single part, it is analysis of a total communication system including transmitter, receiver and channel. Now coming to the channel. The propagation medium or electromagnetic path connecting the transmitter and receiver is called as a channel. In some we have to call it as this is interface medium between transmitter as well as the receiver. If the channel may be wired or a wireless, depend upon the category of communication. In general, the communication channel might consist in wires, coaxial cables, optical cables, and in the case of radio frequency links, waveguides, the atmosphere or empty space. If it is a wireless communication, we are supposed to use coaxial cable, fiber cable and wires. If it is wireless communication, we are supposed to use waveguides, atmospheres and empty space as a communication medium between transmitter and receiver. For most of terrestrial communication links, the channel space is occupied by the atmosphere and partially bounded by the earth surface. For a satellite links, the channel is occupied mostly by the empty space called as a free space. Although some of atmospheric effects occurs at altitudes up to 100 kilometers. The bulk of the atmosphere extends to an altitude of 20 kilometers. Therefore, only the small part, that is 0.05% of the total synchronous altitude of 35,800 kilometers. That means in the 35,800 kilometers, we are supposed to use only 20 kilometers, that is the 0.1% of small part. It is occupied the significant amount of atmosphere. Most of the chapters present link analysis is contents of such a satellite communication link. Here, the link budget issued an extended of terrestrial violation communication links. The propagation medium of the communicated channel between the transmitter and the receiver we can be called as a channel. Coming to the concept of a free space. The concept of a free space assumes a channel free from all to RF propagations such as absorption, reflection, refraction or diffraction. If there is any atmosphere in the channel, it must perfectly uniform and meet all the conditions. Also, we assume that the Earth is infinitely far away, or that is the reflection coefficient is negligible. The RF energy arriving at the receiver is assumed to be a function only the distance from the transmitter following the inverse square law are used in the optics. A free space channel characterizes an ideal RF propagation path. In practice, propagation through an atmosphere and near the ground results in absorption, reflection, diffraction and scattering, which modify the free space transmission. Atmospheric absorption is treated in the next sections, reflection, diffraction and scattering, which play an important role to determine terrestrial communication performance. Once again I repeat, reflection, diffraction and scattering, which plays an important role in to determine the terrestrial communication performance. Now we discuss about error performance degradation. It is established that there are two primary causes for the degradation of error performance. The first is loss in signal to noise ratio, and the second one is signal distortion, as might be caused for intersymbol interference. We discussed in the previous chapters. Some of the equalization techniques to counter the degradation effects of intersymbol interference are treated. Here we are concerned with the bookkeeping of gains and losses signal power and interfering power. Intersymbol interference will not be included in the link budget because it is uniqueness of ISI is that increase a signal power will not always mitigate the degradation and its causes. For a digital communication, error performance depends on the receiver EB by N naught, which can define the equation EB by N naught is equal to signal to noise ratio is multiplied by ratio between W by R. In other words, EB by N naught is a measure of normalized signal to noise ratio or S by N. Unless otherwise state, SNR refer to a average signal power and average noise power. The signal can be information signal or a baseband waveform or a modulated carrier. The SNR can be degraded into two ways. The first one through the decrease of desired signal power, and the second one through the increase of noise power or the increase of interference of signal power. Let us refer to this degradation as a loss and noise or interference respectively. Losses occurs when a portion of the signal is absorbed, diverted, scattered or reflected along its routes to the intended receiver. Thus, a portion of the transmitted energy doesn't arrive at the receiver. Therefore, several sources of interference, electrical noises, and interfering produced by the variations of mechanism and sources, such as thermal noise, galaxy noise, atmospheric noise of mechanism, noise, switching transients, intermodulation noise, and interfering signals from the other sources. Industry use of a term loss and the noise frequently confuse the underlying the degradation mechanism. However, the net effect of SNR is the same. Now we discuss about the sources of signal losses and noise. Basically, nearly 21 parameters are the sources for the signal loss and noises in the either maybe in a wireless communication or a wired communication. So we discuss each and every source in detail. So we start from the band limiting losses. All systems use filters to ensure that the transmitted energy is concerned to the allocated or assigned bandwidth. This is avoid interference with the other channel or user to meet the requirements of regularities agencies. Such filtering reduces the total amount of energy that would otherwise have been transmitted. The result, loss in the signal. So indirectly, due to the limiting of the band, there may be forming of loss indirectly. Due to the limiting of a band of frequency, there is a forming of a loss that is called as a band limiting loss. Coming to the second one, inter-symbol interference. Filtering through the system in the transmitter, in the receiver, and in the channel can result in ISI. The received pulse overlap one other, that is, the tail of one pulse seams into adjacent symbols intervals so that interference with the detection process. Even in the absence of thermal noise, imperfect filtering, system bandwidth constraints, and fading channels leads to inter-symbol interference degradation. It is the second source to generate the loss and the noise. Now coming to the third one, local oscillator phase noise. When a local oscillator is used in signal mixing, phase fluctuations or jitters adds phase noise to the signals. When used as a reference signal in a receiver correlator, phase jitters can cause detected degradation, hence a signal loss. At the transmitter, phase jitter can cause out of band signal spreading, which in turn will be filtered out and causes noise in the signal or loss in the signal. It is also one of the reasons to forming the loss in a signal. And coming to the fourth one, AM by PM conversion. Amplitude variations we can be called as. AM to PM conversion is a phase noise phenomena occurring in non-linear devices such as traveling wave tubes, signal amplitude fluctuations, that in the field we can be called amplitude modulation. These amplitude fluctuations produces phase variations that contribute phase noise to signals that will be coherently detected. AM to PM conversion is also cause extraneous sideband resulting loss in a signal. This is also one of the reasons to produce the loss. And coming to the fifth one, limiter loss and enhancement. A hard limiter can enhance the stronger of true signals and suppress the weaker. This results in either a signal loss or a signal gain. It is more effect of signal loss and signal gain. Coming to the sixth one, multiple carrier intermodulation products. When several signals having different carrier frequencies are simultaneously present in nonlinear devices, such as TWT, traveling wave tubes, the result is a multiplicative interaction between the carrier frequencies, which can produce signals at all combined of some and different frequencies. The energy appropriated to these Soprius signals represent a loss signal's energy. In addition, these IM products appear with the bandwidth region of these or either signal. The effect is that added to the noise of those signals. Coming to the next one, modulation losses. The link budget is a calculation of received useful power. Only the power associated with information bearing signal is useful. Error performance is a function of energy per transmitted symbol. Any power used for transmitting the carrier rather than the modulating signal is a modulation loss. However, the energy in the carrier may be useful in aiding synchronization. And coming to the next one, antenna efficiency. Antennas are transduced to convert electronic signal into electromagnetic fields and vice versa. Electronic signals into electromagnetic fields in the transmitter side, electromagnetic signals into electrical field in the receiver side. They are also used to focus on electromagnetic energy in a desired direction. The larger the antenna aperture, the larger in the resulting of signal power density in the desired direction. An antenna efficiency is described by ratio of its effective aperture to its physical aperture. This mechanism contributing to a reduction in the efficiency or loss in a signal strength are known as amplitude tapering, aperture blocking, scattering, re-radiation, spillover, edge diffraction, and dispersive losses. Typical, typical efficiencies due to the combining of effects of this mechanism range between 50 to 80%. Coming to the next one, that is radome loss and noise. A radome is a protective cover used with some antennas for shielding against the weather effects. A radome being in the path of the signal will scatter and absorb some of the signal energy, thus resulting in the signal loss. A basic law of physics holds in the body capable of absorbing energy and also radiating energy. Some of the energy falls in the bandwidth of the receiver and constitute injected losses. So this is regarding about radome losses and noise. And coming to the next one, pointing losses. These are the loss of a signal when either transmitting antenna or receiving antenna is imperfectly pointed. Once again I repeat, these are the losses of the signals when either transmitting antenna or receiving antenna are imperfectly pointed. So due to this, pointing losses are formed in the communication. And next one, polarization losses. The polarization of electromagnetic fields is defined as the direction of the space along which the field's line point, and the polarization of antenna is described by the polarization of its radiated field. There is a loss of signal due to any polarization mismatch between the transmitting and receiving antennas. And coming to the next one, most important and unavoidable losses, that is atmospheric losses and noise. The atmospheric is reasonable for the signal loss and is also contributor of unwanted noise. The bulk of atmosphere extends an altitude approximately 20 kilometers. At within the relatively short path, important loss and noise mechanism are at work. The atmosphere also contributes noise energy into the link. As in the case of radome molecules, the absorbed energy is also radiated energy. The oxygen water vapor molecules radiate noise throughout the RF spectrum. The portion of the noise that falls within the given bandwidth of given communication system will degrade its SNR. A primary atmosphere causes of a signal loss and contributor noise is rainfall. The more intense of rainfall, the more signal energy is absorbed. And also, on a day when rain passes through an antenna beam, larger amount of atmospheric noises radiated into the system receiver, and there is no clear day. More will be said about atmospheric losses in the next section. And the next one, space loss. There is a decrease in the electrical field strength and thus the signal strength, like power density or flux density, as a function of distance. For a satellite communication link, the space is the largest and single loss in the system. It's a loss in the sense of all the radiated energy is not focused on the intended receiving antenna. Once again, I repeat, it is a loss in the sense of all the radiated energy is not focused on the intended receiving antenna. So this is called as a space loss. And coming to the next one, adjacent channel interference. The interference characterized by unwanted signals from other frequency channels spilling over or injecting energy in the channel of interest. The proximity with the channels can be located in the frequency is determined by modulation spectral role of the width and the shape of the main spectral lobe. And coming to the next one, that is co-channel interference. The co-channel interference refers the degradation causes by an interfering waveform appearing with the signal bandwidth. It can be introduced by variety of ways such as accidental transmission, insufficient vertical and horizontal polarization discriminations, or by radiation spillover from an antenna sideband. It can be brought about the other authorized user of the same spectrum. It is also one of the main reasons to produce co-channel interference. And the next one, intermodulation noise. The IM produced to describe results from the multi-carrier signal interfacing in a non-linear devices. Such a IM products, as sometimes it is called active intermodes. They can either causes a loss in energy or be responsible for noise injected into a link. Here we consider positive intermodes. They are caused by multi-carrier transmission signals interacting with the non-linear components at the transmitter output. This non-linear generally occurs at the junction of waveguide, coupling joints, and corroded surfaces, at the surfaces having pure electrical contact. When large EM fields imping on the surface that have diode like transfer functions, they causes multiplicative products and hence a noise. If such a noise radiated into a closely located receiving antenna, it can seriously degrade the receiver performance. And the next one, galactic or cosmic star and terrestrial noise. All the celestial bodies such as the stars and the planets radiated energy. Such noise energy is the field of view antenna will degrade the SNR, that is signal to noise. And the next one, feeder line noise. The level of the receiver might have very small, that is 10 to the power of minus 12 watts, and thus will partially susceptibility to noise degradation. The receiver front end, therefore, is a region where the great care is taken to keep the noise as small as possible until the signal has been suitably amplified. The waveguide or a cable between the receiving antenna and receiver front end contributes both signal attenuation and thermal noise. Discussed in later. Next one, receiver noise. This is a thermal generated with the receiver. We discussed in the later. And the next one, implementation noise. The noise is in performance Now, implementation loss. The loss of performance and the difference between the theoretical detection performance and actual performance due to the implementation and imperfections such as timing error, frequency offsets, finite rise and fall times of the waveforms and finite value of arithmetic. So this is regarding about implementation losses. And the last one, imperfect synchronization difference. When the carrier phase, the subcarrier phase and the symbolic timing references all are derived perfectly. The error probability as well as defined function of EB by N naught, in generally, they are not derived perfectly. It results a system loss and indirectly the carrier phase and subcarrier and symbolic time references must be perfected. If there is any drawback, if there is any mathematical analysis error, there is a forming to decrease those values turns into perfectively to imperfectively, that results imperfect synchronization reference loss. These are the different sources and signal losses and noises reason for reasoning in the communication. Starting from the first one, band limiting loss, intersymbol interference, local oscillator phase noise, AM by PM conversion, limiter loss and enhancement, multiple carrier intermodulation products, modulation loss, antenna efficiency, radon loss and noise, pointing loss, polarization loss, atmospheric loss and noise space loss, adjacent loss interference, co-channel interference, intermodulation noise, galaxy noise, field feeder line noise, receiver noise and implementation noise and imperfect synchronization reference noise. By observing this block diagram of satellite communication link, emphasizing the sources of signal noise and noises. In this figure, signal noise discussed from the noise sources by a dot pattern or a line pattern respectively. The contributes of both signal noise are identified by a cross-hatched line patterns. And see this losses formation in the overall communication path from the information source to information source, from transmitting to receiver. From the transmitter, there is a formation of band limiting losses, AM by PM conversion losses, multiple carrier product losses, modulation losses, efficiency losses, and radon losses. So these are the losses are related to the transmitter. Coming to the channel, plotting losses, polarization losses, atmospheric losses, phase losses, and pointing losses. From the 10 to 10, those can be considered as channel losses. And coming to the receiver, there is a forming of adjacent channel interference losses, co-channel interference losses, IM losses, radon losses. Radon losses is occurring both transmitter and receiver. Why? Because we are separately using antennas in transmitter side and the receiver side. And similarly, galaxy losses, feeder losses, receiver losses, LO phase losses, band limiting losses, implementation losses, and noise synchronization reference losses. So these are the losses we can be segregated based on occurrence with respect to transmitter, with respect to receiver, and with respect to channel. In the shown figure, we have observed that analog and digital representation of a signals, analog signal plus noise and digital signal plus noise. Analog signal adding some noise disturbance and digital signal adding some noise disturbance. See the variations. When the noise is occurred, every receiver may be using some thresholding passing event. So based upon the thresholding passing event, we can remove the noise based upon the thresholding. See that those amplitude levels are crosses the thresholds, we can be called as a noise. Those are below the threshold level, we can be called that is a signal. So based upon the thresholding concepts also, we can remove the noise in the system. Now we discuss about a small multiple choice questions on noise, which we are discussed in the previous. First one, two functions are called to be orthogonal if on integrating the product we get 1, 0, infinite and none of this. As answer is B. Two fluctuations are called or orthogonal if your integrated values the product is equal to 0. So this one same happen whether we check the particular receiving is signal or error. At the receiver side we are using the same concepts, that's why I am repeating these bits. And coming to the next bit, eigenfunction are not orthogonal. Say it may be true or false. The answer is false. Why it is false? An important property of eigenfunction is that they are orthogonal. Eigenfunctions must be orthogonal. Next bit, based on short noise. Short noise is produced by electrons, photons, electrons and protons and none of the above. Answer is C. It can produced by both electrons and neutrons and protons. So that's why we can be called as this is the electronic loss that can be formed in the non-linear devices. And one more bit regarding about the short noise. Short noise is avoidable when current is 0, 1, C is the infinite and D is the none of the above. Answer is 0. Short noise is avoidable when the current is equal to 0 in the component. And one more bit on the noise, that is which occurs due to equilibrium fluctuations. One is with respect to thermal noise, B is with respect to Johnson noise, C is with respect to thermal and Johnson noise, and D none of the above. Answer is C. Thermal noise occurs due to the equilibrium fluctuations of equilibrium fluctuations. This noise is also called as a Johnson noise. So Johnson noise is also called as a thermal noise due to the equilibrium fluctuations. And this is one of the noise regarding about flicker. Flicker noise is also called as a white noise, pink noise, brown noise and none of the above. And answer is pink noise. Flicker noise is also called as a pink noise. These are the different types of noises. So forming in the different blocks in the communication. Just for the revision purpose, we discuss these 5 bits. In the next session, we are going to be discuss a 10 to 15 number of a multiple choice based upon the topic. Thank you.